Hi everybody, welcome back. Hope you're doing well. Today we're finally going to go ahead and jump in and start learning about these propulsion systems. In my opinion, things will start to get a little interesting. I should make a note that the reference for this course material is Professor Brian Cantwell's course reader for I can't remember if it's AA 210 or what the course name is or course number is at Stanford, but it's a Stanford University course. It's freely available online. It'll be linked in Canvas, or if you're just watching this on YouTube, you can probably Google it and find it. Yeah, so if you're looking for a written reference for this material, that's where you can find that. To get started on this propulsion topic, we're going to go through the engine labeling scheme that we'll use. So one thing I like about Professor Cantwell's text is that he uses consistent labeling throughout, even when propulsion systems have more components or less components. He's still labeling them the same way. Which I think cuts down on confusion quite a bit. So what I'm going to draw is actually the most complex engine that we will cover, which is called a turbofan. And I'll label all the components of that device, and we will be able to go from there as we build up the ramjet, which is our first propulsion system that we will analyze and is also the most simple version. So here's a diagram of a turbofan. Oops. So what I'm going to do is I'm going to draw this very large housing. Okay, and then there's a internal components that goes through here. Okay, and that continues forward until it has a converging diverging nozzle at its exit. Okay, and this guy has these sort of big, just drawing these as like almost big propellers, but it's actually like turbine blades. Okay, and so let's see, let me move it a little bit to the left so I can label the free stream, which is our first label. So the label 0 refers to the free stream. Okay. And then usually we have an inlet, okay? And the general inlet, we sort of draw it with this, just a sort of a miniature converging diverging section, okay? And the front edge of the inlet is labeled station 1, okay? The throat of the inlet is labeled state 1.5. Okay, and then the stage that's directly upstream of the compressor stage, which I'll draw here. So we draw compressors and turbines within the engine with these vertical lines, okay? And that's what we call C for compressor. And then this is connected to a turbine over here. And we'll go through all the details of these components in a bit. This will all make sense. This is the turbine. And so the station that's directly upstage of the compressor, upstream of the compressor, is stage 2. Okay, that's the general rule. So whatever state is hitting the face of the compressor, we'll call that station 2. There's also a burner in between the compressor and the turbine, which we denote with these chevrons, okay, that denotes a burner. We'll label that B for burner. The stage upstream of the burner, sort of in between the compressor and burner, is stage 3. And then in between the burner and the turbine that's stage 4. Okay, and then the stage just downstream of the turbine is stage 5. Okay, we can also have an afterburner, and so the afterburner is located downstream of the turbine. Okay, right here, and then the sort of temperature directly downstream of the afterburner is 6. Okay, and then there's another. At the start of the diverging section, we call that stage 7. Okay, the throat of the nozzle at the exit is stage 8. Okay, so that's the throat, and then we have the exit, which we just denote E. Okay, now there's also this stream that goes around the main core flow. Okay, in the turbofan, and that's called the fan flow. And so we would say there's some m dot fan going through that the fan, and directly downstream. Oh, right. And then the fan, it's also a type of compressor. We denote that 1C. Okay, so the compressor we're labeling with just a lowercase c. The fan we're denoting with 1C. At the start of the converging part of the exterior flow, that is stage 1, 3. So in the same way that the stage 3 was just downstream of the compressor and the core flow, stage 3 is just downstream of the big fan and the fan flow. The throat of the fan flow channel is station 1-8. Okay, and then the exit is station 1E. Okay, so we just put a 1 in front, and so of the fan flow, and then of course we also have m dot core, which is the mass flow area of the air that is going through the core flow. Okay. We'll learn about the specifics of the split between the fan and core flow with the turbofan in a later lecture. But for now, this is sort of the most labels that you'll see, and so we'll continue to use these labels. So even when there's no compressor and turbine, say, in the case of the ramjet, we're still going to have temperature 4 be downstream of the burner. Okay, and you'll see that in just a moment when we start to develop those things. Okay, so this is our most general diagram here. There's also this notation, which I'll just call ratio notation. And it's a nice sort of convenient way of writing this. I'll sort of slowly transition to writing things in terms of these ratios more and more as we move through the lectures. But what the ratios are defined as is tau, okay, is the ratio of the stagnation temperature leaving a component to the stagnation temperature entering the components. Okay, and then pi is the same thing, but it's with stagnation pressure. So it's stag pressure entering components divided by the same thing, but leaving. Oh, whoops, sorry. The numerator is leaving components. The top, leaving is always on the top, and then entering is on the bottom. Entering component. Okay, so some examples of this. We have tau T is the temperature ratio across the turbine, which using our engine labeling scheme is T T5 over T4, okay? And it's always going to be TT5 over TT4 because that's the way the notation works. So the turbine always is split between temperature or station 5 and 4. You know, for continuing along this line, we have the pressure ratio across the compressor is always PT3 over PT2, okay? And you can also do sort of a composite ratio where you might just say like the stagnation pressure difference across a nozzle, say, for example, and it would be like PTE versus PT7 divided by PT7. Okay. Now there's a couple of special ratios. One is tau F, which I think we might have defined in the previous lecture briefly. It's your fuel enthalpy, just divided by CPT naught. Okay, it's just another way of writing the fuel enthalpy in a non-dimensionalized way. But we also have tau lambda, which is defined as TT4 over T naught. Okay, and so it's basically just another way, a non-dimensionalized way of writing TT4. And TT4 is a really important value in the engine. So all engine performance measures essentially improve as TT4 increases. So all performance metrics improve as TT4 increases. And this is so important that, you know, much of the effort in R&D and propulsion systems has been spent making turbines heat resistant. So that temperature, the stagnation temperature at station 4, that's the stagnation temperature the turbine sees is at its face. And so we want to push that to as high a value as possible. And so that's why, you know, a lot of that research effort has gone in that direction. We also have tau R, or you can think of it as tau reference, is equal to TT naught over T naught. And then pi R, likewise, is PT naught over P naught. And both of those things are just a function of the fruit stream Mach number or your cruising speed, right? And so it's they're just reference values. Okay, so there's our engine labeling scheme, a couple of those ratios, and like I said, I don't even think in this lecture we'll be using the ratios very, very much, but as time goes on, you'll see them sneak into more and more of our expressions. Okay, so now let's go ahead and finally get started with the ramjet. And what we're going to do is, following Professor Cantwell's development of this topic, we're actually going to build or develop the ramjet concept one step at a time from ground level. Okay, so let's start with just a inlet, a constant area sort of a engine, let's say, but it has a variable area inlet, and then it has a burner. So it looks like this. It's just kind of like a flat channel, but it has an inlet like this. And keeping with our convention here, we have station 1.5 is at the throat, and then we have station 2, and then station 1. And then, of course, we have our upstream conditions. Again, I need to make sure I leave some room for those. Like that. So we have our upstream conditions of M naught and 3, so we're supersonic. We'll have T naught be 216 Kelvin, and then our stagnation temperature, therefore, in this case, would be 604.8 Kelvin. Okay, so we, of course, we can calculate that knowing what the static temperature is and the Mach number. Then we have a burner here. Directly upstream of that burner is going to be station 3, and then downstream of that burner is station 4. Okay, and then at the exit plane, we're going to put E for exit. Okay, so what we're going to do is we're going to add heat such that we just get to the point where the Mach number at station 4 is just about touching Mach 1. Okay, so suppose just enough heat is added in the burner, so between stations 3 and 4, to reach M4 equal to 1 plus epsilon, where epsilon is some very, very small number. Okay, so once again here, let me adjust this for a second. Okay, so think about this is Rayleigh flow, right? So for Rayleigh flow, if you're starting supersonic, if you add heat, you actually slow the flow down, right? And we actually will use those Rayleigh flow equations. So from Rayleigh is really what I should say. From those Rayleigh flow equations, we will find that PT4 over PT3 is equal to 0.292 in this case. And we also have that TT4 over TT3, which we can write as tau over the burner, just as we could have written the pressure difference as pi over the burner, is equal to 1.53. Okay, and then that tells us that TT4, in this case, is equal to 924.5 Kelvin. Okay, so let's look at if we were to plot the Mach number over this device, it would look like this, right? So this is like, X along the engine axis, and then we have M. So we're going to start at 3, and it's going to, as it enters, it'll decrease a little bit, and then go back up to 3, because this is sort of we're assuming that the flow is adiabatic in that nozzle. So it's just going to slow down as you decrease the area, and then it'll go back up to Mach equal 3. It'll be constant up until it encounters the burner, and then through the burner, it'll go down to Mach number of 1 here, and then go straight out the exit. Okay? So that's what the Mach number is doing, just to be clear. This is station 4, station 3, and then this is station 2. Okay. Now here's one of the more important relations that you'll use over and over and over again when you're analyzing these propulsion systems. Is you're going to use continuity, but a very special form of continuity. Okay, so let's derive this. Okay, it's I'm just going to write down what the mass flow rate is in a fancy way. So we'll start out what we always do, which is just rho AV, but let's bring in the ideal gas law equation of state. So rho becomes P over RT. We're also going to bring in the definition of the Mach number. So we have M times the square root of gamma RT. That's V, right? And then we have A, but I'm going to multiply by A star over A star and A over A. So, sorry. So I'm going to multiply by A over A star and A star over A, kind of like this, okay? Because this thing, this A star over A, is in Cantwell's book, he calls it F of M, okay? This is the one thing that'll be quite confusing. Going between our notation that we've developed up to this point and what Cantwell has in his text, because in our text everything is kind of written in terms of A over A star, and so when you go to look up table values, you're going to be looking up like 1 over f of m, okay? And also just the fact that he's just calling this f of m for this sort of like area Mach relation is what he calls it. Okay, so it's fine though. We will get through it, but with this A over A star, we can actually, so we're pulling out the f of m thing and leaving that where it is, taking that to be a value that we know, but we are going to write out a couple of things. First, we're going to bring in the stagnation pressure and stagnation temperature relations, those values. So that's where we will end up with the following. So essentially, if you were to sub in the stagnation pressure for where the static pressure is, you get the following: 1 plus gamma minus 1 over 2 m squared raised to the power gamma over gamma minus 1. Okay, so that's just subbing in for there. We're also going to, perform some cancellations and bring in the stagnation temperature in the same way. So on the bottom, we're going to have gamma RTT times this quantity 1 plus gamma minus 1 over 2 m squared raised to the power negative gamma plus 1 over quantity 2 times gamma minus 1. And a lot of that complex exponent is actually coming from us rewriting the A over A star as well. At the same time, there's a couple things going on here. Well, the A times f of m, we're leaving those alone. And then we also have the rest of that A over A star function, 1 over m times this quantity 1 plus gamma minus 1 over 2 m squared over gamma plus 1/2. And then this exponent here is gamma plus 1 over 2 times the quantity gamma minus 1. Okay, this is all just kind of a bunch of complicated stuff. There's a lot of things are going to cancel here, like the denominator, for example. And what we end up with in the end is a new expression for the mass flow rate, which we can write as gamma over gamma plus 1 over 2, that whole thing raised to the power gamma plus 1 over 2 times gamma minus 1. So just a very, very complicated constant in effect out front there. And then we have PTA over the square root of gamma RTT times f of m. Okay, so why did we do this? We have the mass flow rate in terms of the stagnation pressure and temperature and this function, this area Mach relation function of m, okay? The reason why this becomes very nice is because then if we compare the mass flow rate between two stations, which we know have to be the same, and we assume that gamma is not changing between those two stations, that complicated constant out front cancels, and what you end up with is a kind of a straightforward relationship between the stagnation conditions and the Mach number between two different locations in the engine. You will do this over and over and over again. At any point in your homework, whenever you're analyzing these systems, the first thing that you should really try, or one of the first things that you should try when you really get down to actually doing some algebra and some math, is to equate the mass flow rate between two stations, as long as there's not some sort of a fuel injection happening between the two stations, right? And in which case, you'll often be given the fuel mass rate, or you might solve for or be given the amount, the difference between the flow rate of the fuel mass and the air mass in the engine. Okay, so that's in effect, that's actually a little bit of an aside, this kind of box here. It's like a derivation. But what we will do is we're going to use continuity between stations 3 and 4. Okay, and we're effectively assuming that the mass flow rate injection is really small here, so we're saying they're equal. And what you end up with, because that super complicated constant out front will cancel, is you have PT3, the area at 3, over the square root of TT4, because gamma and R aren't changing, right? Times F of 3 in this case, because we know the Mach number is 3 at station 3, is equal to PT4 A4 over the square root of TT4 times F of M4. Okay, so a couple of things. First off, there's no, up until station 3, it's all adiabatic. And we also will assume it's isentropic, okay? It's just varying area flow. So PT3 and TT, this should be TT3 right here on the bottom of the left-hand side. So TT3 and PT3 are equivalent to PT0 and TT0, right? There have been no shocks or anything to cause either of those stagnation values to change. So the entire left-hand side of this equation, also the areas are canceling here. The entire left-hand side is all known. So we can essentially write PT naught over the square root of TT naught times F of 3 is equal to PT4 over square root of TT4 times F of M4. Okay, so remember that the case that we're interested in here is that we're approaching Mach 4 equal 1 from above. Okay, and also let's make a couple of notes here. So remember, like we just noted above, that F of M is equal to A star over A. Okay, and in general we know that the maximum value of F of M is equal to 1. And we know that it's 1 because of choked flow, right? So we can't make the area any smaller than A star because we're not going to be able to push the flow to any higher speed than that. Okay, so the flow is choked, and so if we wanted to add any more heat, okay, beyond this point, we're going to cause an issue, because we would need, if looking at this relationship here, if we want to increase TT4 any further, then we would need to have an increase in F of M4, okay, but that is locked at its maximum value. So then we need an increase in PT4, okay, and in order to get an increase in PT4, a shock is going to form, okay. So if we want to add more heat, PT4 must increase. And when I say more heat, what I mean is TT4 is going to go up. That's what I mean by adding more heat. Then PT4 must increase as well, since everything on the left-hand side of the equation is fixed, and F of M4 is maximized. It's sort of stuck, okay? So a shock forms. And this is called the engine unstarting. And engine unstarts. Okay, so now we actually have a shock at the exit of the diffuser. And what this looks like is the following. So same, engine as before, but now we have a shock right here at the exit of the diffuser, where M2 is equal to 3, but M3 upstream of the burner here is equal to, via the normal shock tables, 0.475. Okay, and we still have TT4 equal to this same sort of value. We just went beyond that point. So TT4 is the same 924 value that we calculated before. So 924.5 Kelvin. Okay, so now the pressure ratio between the station 3 and the free stream is not equal to 1, because something is there's a non-isentropic process happening between, or shock happening really, to be precise, between the free stream and station 3. And so this is now equal to 0.3285. And then the stagnation pressure difference across the burner is equal to 0.889. But if we look at what the stagnation pressure difference from the free stream to the stagnation pressure directly downstream of the burner, we're actually going to get the same values before, 0.292. Okay. And also, we know that TT4 is going to be the same as before, like I just said. And the reason for that is because the stagnation temperature does not change across the shock. Okay. So then, now we have this system. And I should draw what the Mach number is doing, just to give you a sense of the dynamics. So like before, it starts at 3, it goes down and back up to 3, but then it sharply drops where the shock is located, down to a subsonic value, and then it goes to where to the entrance of the burner, and now it speeds up to Mach equal 1 through the burner. Okay. So that's Mach number 1 there. And that's what the Mach number is doing. Now let's what about the thrust? What can we compute the thrust for this system? Well, we defined thrust, the non-dimensional form of thrust in the previous lecture, as gamma m naught squared, and this is for the case where our fuel ratio is very small. UE over U naught minus 1 plus AE over A naught times PE over P naught minus 1. So we know that, first of all, this ratio is 1, so we don't have to worry about that. We can actually calculate this pressure ratio using the stagnation conditions and the Mach numbers. So we know that the Mach number at the exit is essentially 1. PTE, whoops, PE over P naught is equal to PTE, PT naught, this whole entire quantity, 1 plus gamma minus 1 over 2, M naught squared over 1 plus gamma minus 1 over 2, ME squared. That whole thing raised to the power gamma over gamma minus 1. This ends up being 5.66. Okay, and then we can get the velocity ratio between the exit and the entrance by first calculating what the temperature ratio is. So if we look at TE over T naught, we can do it the same way that we just did it for the pressure ratio. So TTE over TT naught. So TTE is the same as TT4, so we know what that value is. We know what TT naught is. We know that M naught is 3 and the M at the exit is 1. So then if we put those values in to this relationship, 1 plus gamma minus 1 over 2 ME squared. This time we don't have to use any exponents because this is just the stagnation temperature. In this case we get 3.57. And then if we use that, we can calculate the velocity ratio by using this relationship, which is just the definition of the Mach number. And we get 0.6295. Okay? So then let's calculate the thrust. The thrust, the non-dimensionalized thrust, is equal to 1.4 times 9, so that's the M naught squared, times this 0.6295 minus 1 plus 4.66, and what we end up with is 0. It all cancels out. Okay, so this engine that we've produced here is not producing any thrust at all. Not ideal, but let's go ahead and move in the direction of this thrust. Okay, so what we can do is, the first thing that we should do is we should reduce the throat area until the flow is essentially getting choked in the actual throat, right? Meaning the throat of the diffuser upstream. So this allows us to increase the heat addition without violating mass conservation, because the inlet is now slowing the flow down a little bit instead of the shock. Okay, so as we wanted to add more heat, what was happening is we were creating this shock, right? Well, the shock was occurring at the exit of the diffuser or the inlet, and that was causing a very strong shock from Mach equal 3 down to 1. But ideally, we would want that shock to happen with a lower upstream Mach number, right? And so what we can do is we can try to decrease the minimum area of the diffuser further, so that we're actually slowing down the flow more with the diffuser upstream of the burner than doing it with an actual shock, which is where a lot of the losses are coming from. Okay, so let's see. Like I'll draw this sort of intermediate step here. So what I mean by all the words I just said is that we're decreasing this area. Oh, that's a little extreme. We're decreasing this area here. Wow, that's so bad. This area here. Okay, and we moved the shock to sort of upstream here. So the upstream value of the shock is less than 3. Okay, and the downstream value in this case would be 0.475. Okay, and then TT4, we can now increase it all the way up to 1,814.4 Kelvin. Okay, this configuration produces T over P naught A naught equal to 5.45. Okay, and this all has to do with lower stagnation pressure loss across the shock. So this is weaker shock. Fewer losses. Okay, so that's what's going on there. Let me quickly, just to kind of maintain consistency here, let's draw what the Mach number is doing in this case. So we're starting at 3 like we did before, but now you're decreasing to a lower Mach number that's closer to 1. So let's say, like, we'll do 1 here. We're going very close to 1, then back up, and then having the shock from this lower value down to here, and then going over the burner, heating back up to 1, and then going to the exit. Okay? So after this point, what we can do is we can add a converging nozzle. Keeping the heat addition constant. Whoops. Okay, so what are we doing? So if we look at the mass balance between the throat of the diffuser, the upstream, with the exit, what we'll have is the following. So we have 604.8. That's the stagnation pressure upstream, or temperature upstream. We have the stagnation pressure at the exit, and then AE over, and then we're going to keep the heat add constant. So the stagnation pressure or temperature is going to be what we achieved before. Okay, after decreasing that throat of the that throat area of the diffuser, and we're reducing this guy. Reduce that. Okay, what effect is this going to have? Okay, so in effect, we are decreasing the required stagnation pressure drop. Okay, so because AE is getting smaller, that allows PTE to be the stagnation pressure drop, the stagnation pressure downstream of the burner to be higher. Therefore, the overall drop is lower. Okay, so PT drop is reduced. So the shock is moving backward toward the inlet. Okay, and then eventually hits the inlet throat, and disappears. Okay. And this is the operating at the third critical of the diffuser or inlet. Okay, so what does this look like? We have our straight channel that we had before, but it just tapers off at the exit. We have our burner, and then our inlet here, and now we have no shock occurring. And the Mach number entering the burner is actually very small now. It's 0.138. So we slowed the flow way down upstream of the burner. And the Mach number through this system looks like this, where you have start at 3 like you did before, but you smoothly go down to that subsonic Mach number. You can count to the burner, speed back up to 1, and then go to your exit. Okay? So because one common assumption, just as a little aside here, and we'll sort of justify this assumption later. One common assumption is that the pressure difference, the stagnation pressure drop across the burner is basically 1. Okay, that it's not changing across the burner. If we use that assumption, we get that T over P naught A naught in this case is 6.034, which is a 20% improvement just from reducing the area. So about 20% improvement by reducing AE. Okay, getting rid of that shock. Okay, so far we had this straight channel. We increased the heat addition until a shock appeared. Then we shrunk the area of our inlet to slow down the flow a little bit more, and then we added a converging nozzle at the exit that allowed us to move that shock all the way into the throat of the inlet where it disappeared, and now we don't have a shock, and we have this smooth decrease of the speed through the diffuser operating that third critical, and no shocks in the system, and we have this thrust of 6.034. So that brings us to the ideal ramjet. Okay, and what we're going to do is we're actually going to convert that enthalpy that we got from the burner, now that we've increased that heat to this high value, we're going to convert that to more speed with a diverging section of the exit. Okay, so what that looks like is you have the straight, and then you're going to have a converging diverging nozzle at the exit. We have our inlet that slows down the flow. We have our burner, and then we have our throat here, E, or 8, and then the exit is here. Okay? So here's what we'll do. We're going to choose AE over A naught, or sorry, AE over A8 such that we are perfectly expanded, or that PE over P naught is equal to 1. Okay? And then we're also have our burner assumption that we just mentioned before, that P or pi B is equal to 1. So what we can do is we can calculate PE over P naught and see that PTE over PT naught in this case is this is going to 1. That's our assumption. And then we have this ratio here, 1 plus gamma minus 1 over 2 m naught squared over 1 plus gamma minus 1 over 2 m exit squared. And we know that this is equal to 1 because we're assuming that we're choosing that area ratio such that that perfect expansion happens. And so this thing also tells us that ME is equal to M naught. Okay, so that's a bit of a derivation of that. And then we can calculate TE over T naught, which is TTE over TT naught. We know what that value is. And then we know that whatever is in this bracket here is just going to go to 1, so the Mach numbers are the same. So TE over T naught is equal to TTE over TT naught, which is equal to 3 in this case. Okay, and now we can recalculate T over P naught A naught, and it's equal to gamma M naught squared times ME square root of TE over M naught square root of T naught minus 1, and the perfect expansion gets rid of the pressure term in that equation, and we end up with 9.22. Okay, so that's adding this divergent section, just adding that alone, increased the thrust by 50%. Increased thrust by 50%. Okay? So this whole time we've actually been assuming that the fuel mass flow rate is very small, or rather that, note, we assume that F is much less than 1. But we should be able to justify this assumption, right? So let's look at the energy balance from last time. And in general, okay, if you're going to be calculating a fuel mass flow rate or doing anything with this lowercase f, you want to go to that energy balance. So we calculated this last time. It's that m dot f, hf, is equal to m dot a plus m dot f times ht4 minus m dot a ht3. Okay? This thing is the same as ht naught in this case, okay, because we don't have any shocks upstream of there's really no shocks in the system at all. And this thing is just ht exit. Okay, and we are going to assume that we're burning JP4 fuel. So we'll know what HF is. And we can divide both sides of this equation by m dot A, and we'll end up with is the following: F times H of F is equal to 1 plus F quantity times HT4 minus HT3. And we can calculate F as HT4 minus HT3 divided by HF minus HT4. HF is just a value we look up. Okay, and if we plug in all of the values that we have from our scenario here, we get 0.0297, which is quite small. And so our assumption that it's very small is good. Okay, so in general, if you're assuming that you have a very small fuel mass flow rate, you should probably loop back in the end and make sure that with all the values that you calculated, you do indeed get a very small number value for F as a way to validate your assumption. Let's go ahead and calculate the efficiency numbers. So the overall efficiency of the ideal ramjet is, using the non-dimensionalized form of the equation, we already have F, tau F. We know what tau F is. That's just HF over CPT naught. We defined that earlier in this lecture. And then we have our non-dimensionalized thrust. We end up with a 0.482 value for efficiency. For the propulsive efficiency, since it's perfectly expanded, we can just look at 2 U naught, or V naught rather, over VE plus V naught, and that's 0.732, okay? And then for the thermal efficiency, we can do it this way. So apologies for the pause there. I just wanted to make sure I understood my notes. So in general, right, the way we can write this is in the following way, where we have m dot A plus m dot F times HE minus m dot A H naught. Okay, that whole thing there is the Q rejected for this ideal ramjet. Okay, and then on the denominator we have Q in, which is m dot A plus m dot F times HTE minus m dot A HT naught. That's Q in. Okay, and what we can do is we can simplify this. You have T naught over TT naught. Okay, and then we have 1 plus F TE over T naught minus 1. Sorry, I'm definitely skipping some steps here. But TT over TT naught. But you can go back and check this if you want. Now we showed before that TE over T naught is the same as TTE over TT naught. So this whole thing goes to 1. Okay, and so the thermal efficiency of the ideal ramjet is equal to 1 minus T naught over TT naught, which is interesting, so keep this in mind for a moment. This is also, we'll compare this to the Brayton cycle, for example, which is 1 minus T naught over T3. So one thing is this T naught over TT naught, you can see that the efficiency only depends on how fast you're going. So that's the first thing. It's just on the upstream Mach number. But one thing to keep in mind is that the Mach number at station 3 upstream of the burner is basically 0. So in our cycle, it's very small at least. Mach number at station 3 is approximately equal to 0. So that means that TT naught is actually approximately equal to T3 in this case. So the ideal ramjet is, you can think of it as identical to the Brayton cycle. That's the reason why I did this exercise of the thermal efficiency. So you can say that ideal ramjet is approximately identical to the Brayton cycle, efficiency-wise. And so, but I will make a note here that this overall design is actually not very practical because the inlet is extremely sensitive to downstream conditions. So like if you slightly increase the heating, for example, like you add more heat, or you decrease your overall speed, you can cause that unstart condition, which you have a normal shock in front of in the frontal region of the engine. Okay, so practical designs usually require some sort of inlet shock for stable operation. So say not practical, prone to unstart, practical designs require inlet shock. For stable operation. Okay, so let's spend a little bit of time here optimizing the performance of the ramjet. And then we'll be done. Okay, so we want to optimize in terms of our engine parameters like tau lambda and tau r. So tau r is just how fast are you going. Tau lambda has to do with your how much heat you're adding, right? So rewrite in terms of tau lambda and tau r. Okay, so from the energy balance, we have that m dot f hf is equal to m dot a plus m dot f times ht4 minus m dot a ht3. We will do some normalization here. So we have f is hf over cp t naught is equal to 1 plus f times tt4 over t naught minus tt naught over t naught. So this thing, that thing on the right there is these two things on the right here are tau lambda and tau r respectively, and we have tau f on the left. And so we can write f in terms of tau lambda minus tau r over tau f minus tau lambda. For the ideal ramjet in particular, don't go kind of thinking this is a general formula for f on all cases, okay? I would encourage you to always go back to the energy balance and do it again, okay? This should work because the burner is always going to happen. But if you have other components pulling energy and transferring energy across the different stations, like a compressor and turbine, which we'll see later, you don't want to use the same sort of expression for F. Okay. So we will also keep in mind that let's see. Oh yes. So this is a way that we can actually rewrite the entire thrust equation. So a couple of note things here. So first off, we know that TE over T naught is equal to TTE over TT naught, right? Which we can rewrite as tau lambda over tau r. Okay, first thing. We also know that ME is equal to M naught. We derived that. And so that allows us to write M naught in terms of, in fact, we can also write M naught in terms of tau. So M naught squared, and I'll just let you check me on this, can just be written the following way. Okay, so that's just a definition. And we can write, using this equation here, we can also write that 1 plus F can be written as, sorry about the handwriting there, can be written as tau F minus tau R over tau F minus tau lambda. Okay? So all of that to say, let's go ahead and just rewrite this thrust equation, this non-dimensionalized thrust value. So it's normally written as gamma m naught squared times 1 plus F times ME over M naught times the square root of TE over T naught minus 1. Okay, that was our thrust equation before. And we can express that in terms of all these engine parameters in terms of all the different taus in the following way, where we have 2 gamma over gamma minus 1 times the quantity tau r minus 1 times this big fat thing here, tau f minus tau r divided by tau f minus tau lambda. Oh geez, this is the taus are starting to look like lambdas. Tau lambda, there we go, times the square root of tau lambda over tau r minus 1. Okay, so Now that's our thrust in terms of those engine parameters, tau. Okay, so let's optimize that with respect to tau r, so how fast you're going, right? Optimize with respect to tau r. And I'll spare you the gory details, and I'll just draw with the plots that we get here. So plotting our non-dimensionalized thrust as a function of tau r, we have 0 thrust at Mach equal 1. Then we have like 2, 4, 6. Our maximum is right around 3.5. So it's like this. We get 0 thrust at 1, it goes up like that. And then I think it goes back down to 0 at like 8 point something. So it'll be like over here. So imagine this is like 8 here. Okay, so that's our thrust. So you can go too fast, let's say. We can also look at the non-dimensionalized specific impulse of this engine. And much like, this is a function of tau r, much like the thrust, it starts at 0, but then it climbs up to a high value here, and then it just kind of decays a lot more slowly. Okay, so the cool thing is that tau r star, so this, whatever this, we'll say this is like, so first of all, this is tau r star. In this case is about 3.5, which corresponds, funnily enough, to a Mach number pretty close to that, which is 3.53. Sorry, 3.53. So that's where the optimal Mach number is. The tau r star that you get for the ISP for the specific impulse is about the same. Tau r star for ISP is almost identical. So that's nice. Whether you're optimizing for, let's say, fuel efficiency or overall thrust. But what if we want to push to higher Mach numbers? And this will be the last note that we leave on here. So we're just going to define really quickly this coefficient of thrust, which is T over basically like your dynamic pressure, the same dynamic pressure force, same thing that we always do for like a coefficient of lift, for example. If we write this in terms of our non-dimensionalized values, we get 1 plus F times the square root of TT4 over TT naught minus 1. Okay. And then we can also figure out what the energy balance, what TTE over TT naught is in terms of these, in terms of M naught, but the punchline is the following. I'm going to draw just these two plots. So I'm going to draw TTE over TT naught and say that it's approaching 1 here. And it goes like this. And then the coefficient of thrust approaches F. Okay. But same sort of behavior in this plot. It kind of dives towards that asymptote as a function of M naught. Okay, so basically thrust is decreasing, overall thrust. Thrust decreases as M naught increases, but your drag is actually approximately constant for high Mach number. So your ramjet is essentially becoming ineffective. approximately constant. So ramjets become ineffective. So we can't push effective. So we can't push the ramjets all the way to say, like hypersonic operation, for example. Okay, so let's see. There is one. So that as far as content, that's the end of the content for today. There is a video about the ramjets that I will link in the. Normally, I would show it during the lecture in person, but I'll link it in the description of this video, so you can go ahead and take a look at it. It's kind of interesting. I think it's quite a historical video, but it kind of shows the type of thing, what an actual ramjet looks like, and the type of things that they're used for. But yeah, so next time I think we're going to look at the turbojet. So that should be interesting, bringing in some more complexity into the energy balance there. Hopefully this was relatively enjoyable or understandable. All of these things will become more concrete as you do some of the example problems in your homework, and I think in the future, at least in class, we'll probably have a day or two of examples with these propulsion stuffs, because I remember the first time through this material was a little bit of whiplash for the students. So I may add those to the online lectures later on as well. But oh yeah, one last note. So ramjets become ineffective, and then the way forward in sort of the hypersonic realm is a scramjet. Okay, and we'll discuss those a little bit later. But for now, thanks for taking the time to listen. Hope you learned something, and I will see you in the next lecture. See ya.